Hi, everyone. I hope you and your families are staying safe. It's been a really intense and kind of devastating week. So before we get started with chemistry class, I just wanted to say that Black Lives Matter, and it's long past time that we end police brutality in this country. I really encourage you all to read the news, read about the issues, and make your own voices heard. I'm around during office hours if you want to talk. In the meantime, let's learn some chemistry. All right, go ahead and take a couple minutes to pause the video and answer this do now question. Okay, so we're given this chemical reaction, which is a redox reaction. We want to know the products of this chemical reaction. This is a single replacement reaction where the zinc is going to react with the copper and basically replace the copper in this compound. And so you're going to form copper, solid copper, and zinc sulfate. And you can actually see that in this picture. So if you stick a strip of zinc into a solution of copper sulfate, you form this solid copper on the outside of the zinc strip. And so what you see is this kind of darker metal, which if you were to refine it a little bit would look coppery, right? It has that sort of orange color, which of course, like filtered through the blue solution, looks kind of basically just black. And then you'll notice too that the solution becomes lighter in color because the copper ions are being removed from the solution to form solid copper. And so the concentration of copper ions goes down. Zinc ions, which we're forming, are clear. And the copper ions, which are blue, their concentration is decreasing. Cool. We want to know the oxidation and the reduction half reactions. The oxidation half reaction would be zinc reacting to make zinc 2+ plus 2 electrons, right? We know that oxidation is loss. So the one that loses the electrons, in this case zinc, that's the oxidation half reaction. Reduction is gain. So the element that's gaining electrons is getting reduced. That's copper in this case. So copper is going from 2+ to neutral and gaining 2 electrons. So that's our reduction half reaction. And then to write the net equation, we can realize that zinc sulfate is really Zn2+ plus SO4 2-, right? The ions split apart when they're in solution. Same with copper sulfate. Copper sulfate is really Cu2+ and SO4 2- split up in solution. And so the sulfate is entirely a spectator ion in this reaction. It's not reacting at all. And so we can leave that off when we're writing the net equation, which would look like this. You can include the states if you'd like. But essentially, solid zinc is reacting with copper ions to form zinc ions and solid copper. Cool. Let's talk about how a battery works. So a battery is an everyday object. I'm sure you're all familiar with them, right? We have, disposable batteries that you can stick into like a remote or flashlight, and of course, rechargeable batteries like what's in your computer or your cell phone. We know that batteries generate electricity. They power our electrical devices. Electricity is really a flow of charge. Generally in everyday life, we're talking about a flow of electrons through metal wires, right? And so what a battery is doing is it's essentially causing electrons to flow through some sort of circuit. So a battery essentially acts like an electron pump, where the negative end of the battery basically shoves electrons out, and the positive end of the battery basically sucks electrons in. And so the electrons are forced by the battery to move through a circuit and power whatever's attached to the battery. In order to do that, a battery has to use a redox reaction, right? In a spontaneous redox reaction, electrons are being transferred and energy is released. And so that's exactly what's going on in a battery, right? You've got a chemical reaction that is producing electrons and then absorbing electrons again. And it's worth knowing a battery is composed of a bunch of voltaic cells, which are also referred to as galvanic cells. Voltaic cells and galvanic cells are 100% just synonyms. And we're going to talk today about what those are and how to construct them. But that's what a battery is. And so we know that in order to have a battery, you need to not just have a redox reaction, but have a redox reaction that's going to kick off electrons from one side and absorb electrons from the other. Okay, so we saw in our Arduino that one example of a spontaneous redox reaction is solid zinc, which reacts with copper sulfate. So you might think that you could construct a voltaic cell like this, where you have a strip of solid zinc inside a copper sulfate solution, and you can kind of wire up a light bulb to the outside. Now, it turns out that this setup will not work. This will not successfully light the light bulb. So you might want to pause the video for a second, take a minute to think about why this setup is not going to light the light bulb. We have a chemical reaction that's spontaneous, and yet it's not going to work to light the bulb. All right, so you might have heard that current electricity takes the path of least resistance, which is to say the current's going to flow through whatever the easiest path is. In this case, in this chemical reaction, right, zinc is losing electrons and the copper ions are gaining electrons. And so one option of a path that the electrons could take is they could flow through the light bulb and light up the light bulb and then into the copper solution. However, none of the electrons are going to do that because they have a much easier path instead, right? Because the zinc is directly touching the copper sulfate solution, is directly in contact with the copper sulfate solution, it's much easier for the electrons to just directly go from the zinc right to the copper ions. And so this is an example of an unsuccessful voltaic cell. This will not light the light bulb because even though you have a spontaneous reaction, you're not forcing the electrons to actually go through the bulb. The electrons can just directly be transferred. And so in order to have a successful voltaic cell, we actually need to separate the two half reactions so that the only path that the electrons can possibly take is through the light bulb. If we give the electrons an alternative where they can just directly flow from the copper to the zinc, they're going to do that. So let's take a look at an example of that type of setup. All right, so I've pulled up a video that has an example of a voltaic cell. So notice that in this setup, we've separated out essentially our two half reactions. We've separated out the oxidation half reaction and the reduction half reaction. What we have here is we have a copper strip inside a copper sulfate solution. And we also have a zinc strip inside a zinc sulfate solution. So you always keep a strip of the same type of metal inside its own solution. So copper won't react with copper sulfate, right? There's no reaction to be had, and zinc won't react with zinc sulfate. There's no reaction to be had there either, right? So you're not having a reaction within any one beaker. But when we connect the two beakers to each other, when we wire them together, now we can have a reaction. And so what's going on is that you would wire the zinc strip up to whatever your load is, and then you would wire that to the copper strip. So right now, what we have here is a voltmeter, which will read the voltage that we're producing, which right now is 0. But if you wanted, you could, instead of a voltmeter, you could hook up a light bulb or your cell phone or whatever. Cool. Let's talk a little bit about what can happen in this reaction. So we know that the zinc is what's getting oxidized. So theoretically, the zinc strip can lose electrons, which can then travel through this black wire, through the voltmeter, through the red wire, through the solid copper, and then connect with the copper ions that are in this solution. So these extra electrons can be passed to the copper ions in the solution, which could then form solid copper. You'll notice that that's actually not happening right now. We're getting a voltage of 0, nothing's really happening. And the reason for that is that right now we have an incomplete circuit. So theoretically, electrons can flow from the zinc to the copper, But if that happens, this beaker is going to become positively charged. If this beaker gains a whole bunch of electrons, it's going to become negatively charged. And as soon as a few electrons flow from this beaker to this beaker, as soon as this beaker starts to become positively charged, it's going to start attracting electrons back to it. As soon as this beaker starts to become negatively charged, it's going to start repelling electrons. And so a few electrons might be able to flow from one beaker to the other, but very, very quickly, the electron flow will stop. Nothing else can happen because there's a charge imbalance. And so you can't actually have a successful chemical reaction here. You can't maintain a flow of current because the beakers are getting charged, and those charges prevent the current from continuing to flow, right? The positive charge here would attract electrons back into the beaker. The negative charge here would repel the electrons, so they won't keep going into the beaker. And so what we need is we need some way to balance the charges, to keep both of these beakers neutral. Now, we also know that we need the electrons to be flowing through this external wire, right? If we want the current to be useful, if we want this chemical reaction to actually power our light bulb or our cell phone or our voltmeter, right, we need the electrons to be flowing through this wire. And so we need a way to balance the charge between these two beakers without allowing electrons to flow directly from one beaker to the other. Because if we allow the electrons to, if we give them the possibility that the electrons can flow directly, they will, right? They'll just skip out on our voltmeter, and our battery won't work. It won't do what we want it to do. And so what we need is we need a way of conducting electricity without conducting electrons. Cool, we know a way to do that, right? That's to use a salt solution, right? A salt solution conducts electricity by moving around ions without moving around electrons. And so what we're going to do is we're going to add in what's called a salt bridge, which allows ions to flow from one solution to the other without allowing electrons to flow from one solution to the other. That way the electrons are still forced to go through the outside, but we then, once we connect these with our salt bridge, we will have a neutral solution, and we'll have a complete circuit in which the current can flow in a full circle. So let's go ahead and watch what happens when they add the salt bridge.
So we're going to complete that circuit with an ion bridge. An ion bridge is a solution which bridges across the two half cells of the voltaic cell. And notice as we put it in, the reading registers on the voltmeter.
Good, so you can immediately see as soon as we plop in that salt bridge, now our voltaic cell is actually functioning. We're getting just a little over 1 volt of electric potential from this setup. So this setup right here is the basic idea behind every battery, right? You've got an oxidation half reaction, you've got a reduction half reaction, you've got a salt bridge, which conducts charge but doesn't conduct ions, connecting those two reactions, and then meanwhile, the electrons are flowing through this external circuit. Awesome. Okay, so I'm back in PowerPoint. Let's take a look at a schematic of a voltaic cell. So you can see that this is actually almost identical to the setup we had in the video. It's sort of done in cartoon form instead of like an actual live version, but it's basically exactly the same. So we have one beaker with a zinc strip in a zinc solution. We've got a copper strip in a copper solution. They're connected via a salt bridge, and then they're connected externally with a wire. So if this was a battery, this portion, like right here, would all be like inside the battery, and then this wire and the light bulb is what's outside of the battery. Cool. A couple of key pieces of vocabulary. The half cell where the oxidation is occurring is called the anode. So let's go ahead and write the half reaction that's happening at the anode. In this case, the zinc is getting oxidized. That on a battery, the anode is referred to with a little negative sign. And there's a common misconception that the anode of a battery is negatively charged. It's not. The whole battery is neutral. The negative end is neutral. The positive end is also neutral. But the negative end of the battery is the anode, which means it's spitting out electrons. It's getting oxidized, and so it's producing electrons. The other half cell where reduction is occurring is called the cathode. So let's go ahead and write the half reaction that's happening there. In the case of copper, copper is getting reduced, so CO2 plus ions are forming plain copper. So again, the anode is where oxidation occurs, the cathode is where reduction occurs. So oftentimes folks will remember that by remembering anox, red cat. Cool. The salt bridge contains a salt solution, which is what allows ions to flow through to keep the charges balanced. So let's think about which direction ions would need to flow in order to balance the charges. In the anode loses electrons. And so if there were no salt bridge, the anode would be getting positively charged. And so in order to balance out that positive charge, right, from losing electrons, the anode is going to gain some negatively charged ions. So whatever the negative ions in the salt bridge are, which in this drawing is nitrate ions, but whatever the negatively charged ions in the salt bridge are, they're going to flow into the anode. Meanwhile, the cathode, where reduction is happening, is gaining electrons. So if there were no salt bridge, the cathode would be becoming negatively charged. In order to neutralize that charge and balance out, the cathode is going to gain positively charged ions. And so the positively charged ions are going to flow through the salt bridge and into the cathode. So cations move toward the cathode, anions move toward the anode. And overall, each of these beakers, each of these half cells, remains electrically neutral. For every one electron that leaves the anode, one negatively charged ion will enter the anode, or one positively charged ion will leave the anode. Right? For every one electron that flows into the cathode, one positively charged ion will flow into the cathode, or one negatively charged ion will flow out of the cathode. Cool. During the chemical reaction that's happening, the masses of these two electrodes, the anode and the cathode, their masses will actually literally change. Let's take a minute to think about what's going to happen to the mass of the anode and the mass of the cathode. So the anode is getting oxidized. That means that the metal ions in the anode are losing electrons and becoming aqueous ions. And so the anode, the actual strip of metal, is losing mass. It's getting lighter and lighter because essentially, as the reaction is happening, that metal strip is basically dissolving into the solution. Meanwhile, at the cathode's getting reduced. That means it's gaining electrons, and those electrons are going to react with the ions that are in the solution. So if you have a copper cathode, the Cu2 plus ions in the solution are going to gain electrons and form solid copper. And so as the reaction goes on, the cathode is getting fatter and more massive because it's gaining atoms. There's sometimes a misconception that the cathode gains mass because it's gaining electrons. That's actually not true, right? Electrons are essentially massless. They have such a tiny mass that they have no direct effect on the mass of the cathode. We would never be able to measure the mass change because of the electrons themselves. But what's happening is those electrons cause the ions in the solution to become reduced and to go from aqueous ions to solid metal atoms that stick to the cathode. And so the cathode's gaining mass because it's gaining more and more atoms as the ions in the solution get reduced. Cool. Batteries or voltaic cells are sometimes abbreviated in this way, where you show the anode and you show the the reactant and then the product from the anode, whatever's in the salt bridge, and then the reactant and the product from the cathode. This style of abbreviation is just like shorthand. We don't include the spectator ions in either of these two half cells. We just include the ions that are reacting. If we don't know or don't care about the salt bridge, you can also abbreviate it in this way with just omitting the salt bridge entirely. So let's look at a couple of example problems. I want to know the half cell reactions for these two possible galvanic cells. And then I want you to sketch and label a galvanic cell that actually uses this spontaneous redox reaction.
All right, let's go ahead and get started on these practice problems. So we want to write the anode and cathode half cell reactions for these two possible galvanic cells. For this one, we can see the anode has aluminum, solid aluminum, being oxidized to form Al3+, right? So that's going to be our oxidation half reaction for our anode, right? An-ox red cat. And that's going to be that aluminum is going to lose 3 electrons in order to form Al3+. And if you want to, you can include the states, but that's not super necessary. And then our reduction half reaction would be happening in the cathode, right? So An-ox red cat. And that's lead, it looks like lead 2 is being reduced to form solid lead. So in order to do that, it's going to need to gain 2 electrons to form just plain solid lead. And then if we wanted to, if we were going to balance the equation overall, right, we know that we'd have to multiply this reaction by 2 and this one by 3, so that the same number of electrons are being gained and lost. That's not being asked in the problem, so we're done. But if we wanted to write the overall balanced equation, we would have to do that. For the next one, our oxidation reaction at the anode is happening with magnesium. So it looks like magnesium is losing 2 electrons to form a +2 ion. And then in the cathode, we've got iron 2, which has to gain 2 electrons to form elemental iron. Okay, now let's take a look at this last question. So we want to sketch and label a galvanic cell that uses this particular reaction. So I'm going to go ahead and sort of start sketching like a generic galvanic cell. So I'm going to need like 2 containers, 2 beakers essentially, right? One of them is going to have aluminum and one of them is going to have tin. So I'm going to go ahead and draw in a strip of aluminum metal. And then in the other one, I'm going to go ahead and draw in a strip of tin metal, right? And each of those strips of solid metal should be in a solution that contains that ion, right? So this would have to be a solution that contains Al3+ ions and some sort of anion as well to balance that out, right? Maybe we'll say Cl-. It could be any anion, right? The anion's not actually involved in the chemical reaction. And then we've got Sn2+ in this beaker. And so again, we'll need some sort of anion. Might as well just use the same anion. We need a salt bridge connecting these two. So I'm going to go ahead and label this salt bridge. And we might as well, we can put any ionic compound, but I'm going to go ahead and say that our salt bridge has sodium chloride. So I'm going to put in some Na+ and some Cl-. And then I've done a bad job of leaving myself some room, but this metal electrode and this metal electrode would need to be connected. So I'm going to actually draw this like down here below all of this. These would need to be connected via whatever you're trying to power, right? So this would be like your light bulb, or it could just be a voltmeter, which the symbol for that is just a V in a circle. But whatever the external part of the circuit is would go here. this looks pretty good. Let me go ahead and add in a couple of other labels. So we should really label the anode and the cathode. We should write in the half reactions. And I want to also label the direction the ions are moving in the salt bridge. So take a minute, if you haven't done that in yours, to pause the video and do that. Okay, so aluminum is going from solid aluminum to Al3+. It's losing electrons, which means it's getting oxidized. So that means that the beaker with aluminum is our anode, right? Anox. And the tin, which is getting reduced from Sn2+ to just solid tin, is our cathode. The half reaction for the aluminum is that aluminum is forming Al3+ plus 3 electrons. The half reaction for the tin is that tin 2+ is gaining 2 electrons to form solid tin. And so we could also say what's happening to the mass of these 2 electrodes of the anode and the cathode. Take a minute to label that if you haven't already done that. So aluminum, the solid aluminum ions are essentially dissolving into the solution. So the mass of our aluminum strip is going to go down. For tin, we've got ions in solution that are essentially going to form solid tin and coat the outside of this metal strip, this electrode. And so the mass of the cathode is going to increase. And then let's also label what's happening with the ions here. Oh, and the electron flow as well. So we should label the direction of electron flow in this wire. The aluminum is losing electrons. The electrons are going to leave the aluminum, and then the tin is gaining electrons. So the electrons are going to flow from the outside circuit into the tin. So the electrons are flowing, the way I've drawn this, they're flowing left to right in this circuit. Meanwhile, if electrons are leaving this beaker, it would be becoming positively charged. So to balance that out, the negative charge from the salt bridge needs to flow in this direction. So the chloride ions are going to be flowing into this beaker. This beaker is gaining negative electrons. So to balance out that negative charge, the positively charged sodium would have to flow from the salt bridge into this beaker. All right. I think I've labeled everything that I could label. So here's my sketch. It's beautiful. I hope you love it and treasure it as much as I do. Hopefully your drawing is like a little better looking than this.
All right, this is one of my favorite topics because it's really practical. I hope you enjoyed it too, and I will see you next time.